All right, people, welcome to Let's Get to the Marks. We're looking at AS Chemistry here. This is the 2022 paper for Edexcel AS Chemistry, Paper 1, Core and Inorganic Chemistry. So let's go. Question 1. Which is the electronic configuration of a sulfur 2- ion, a sulfide ion? So sulfur in itself, if you look in the periodic table, has a mass number of 32, atomic number of 16. So 16 tells us there are 16 electrons. So we want to write out the configuration: 1s2, 2s2, 2p6. Remember, with each level you go up, you gain a new subshell. So the first subshell only has S, and the second one is S and P, and then the third is SP and D. Now here, this would tell us, oh, sulfur is 3p4 it ends in. So B could be the answer, but that's actually incorrect because it told us here that it was a sulfide ion. What does the 2- mean, peeps? It means we have 2 extra electrons. So instead of 16, we're really pretending it has 18. We're not pretending. And so our answer is 3p6. So we might say, well, surely that means the answer is C then, because that ends in 3p6. Aha, C is wrong. There's something missing. Look at C. It goes 1s2, 2s2, 2p6, and then straight to 3p6. Where's the 3s? So each shell or quantum level starts with the s orbital, and that's missing from that one. So the only possible answer is D, which has the correct amount of electrons. So 1s2, 2s2, 2p6, 3s2, 3p6. So lovely. And that's the answer to question 1. If you're liking the video so far, hit the like, subscribe, make sure you share with friends on your course, because that's going to help me bring more videos to help you. Okay, so let's look at this question 2. Which is the most likely sequence in kilojoule per mole for the first 4 ionization energies of barium? All right, let's look at A. We've got a series of 4 ionization energies, but there's no significant jumps in these ionization energies. Yes, they increase because you get closer to the nucleus, it gets harder to remove an electron, requires more energy. But barium's a group 2 metal, and you can find that out by looking up in your periodic table. And this means that with barium, we're going to be taking away the first 2 electrons, and then the third electron is going to come from a brand new shell. So the third electron, we're going to be breaking into a new quantum level, which is closer to the nucleus and has less shielding, so it's going to require a big jump in energy. So we look at the answer B. When we look at B, there's a huge jump between the first and second. So that doesn't suggest we've already taken away 2 electrons. This looks like a group 1 element where it's easy to take away the first and then you're going into a second shell. If you look at answer C, this is one that suggests a group 2 element. The first 2 electrons are relatively easy, and the third electron is from a brand new shell. And that would tell you it's group 2, because the first 2 outer electrons would be easy to take. When you take the third electron, you're breaking into a full shell that's closer to the nucleus and has less shielding. And that's the way you really find out what the correct answer is. You can see here for D, D looks like a group 3 element because the 4th ionization energy is breaking into a new shell. So that's probably a group 3 element. All right, guys. Let's go. This is one of my first Edexcel walkthroughs, so if you're liking it and you're studying Edexcel and you want me to do more, definitely hit the like. Okay, question 3. This question is about tests for ions. A student wrote the following answer in a question about the processes that can give rise to a flame color during a flame test in an inorganic compound. When an inorganic compound is heated, energy is emitted as ions move up energy levels. Electrons return to lower energy levels and then release energy as light, which is always in the visible region of the electromagnetic spectrum. Identify the 3 errors and suggest the correct word. So the first one, energy is emitted. That's incorrect. In order to move electrons and excite them up the energy levels, energy is absorbed. So the word they needed to use as correct would be absorbed. The second error is ions. You don't excite ions, you excite electrons. And do they always release visible light? No, not always, just sometimes. All right, remember to pause the questions at the start of each question. Press pause and have a go before I whip through the answers, because I tried to go through quick. So make sure you pause these. Which compound does not give a red color in a flame test? Well, calcium's red, lithium is crimson red, calcium's actually brick red or orange red, and strontium is red too. Sodium ions give a yellow flame, so the correct answer here is C. Okay, what wire should we use in a flame test? What material is suitable? Well, copper's not too reactive. We use it in piping, and we use it in cooking pots, and we use it in electrical wiring and water pipes. So it's not that it's too reactive. It's not that it's too reactive. The problem with copper is that copper gives you a blue-green flame when you heat it, and that is going to hide any test you're looking for. That might disguise the color of the test. For instance, if you have sodium there and the copper's giving off blue and green, how are you going to see the yellow flame of the sodium? So you want a metal that doesn't really give off a distinct colored flame. Iron's very reactive. It's going to form iron oxide. The iron's going to rust. Magnesium, you get a bright white light when you heat magnesium. Also, it's very reactive, so you're going to form magnesium oxide, and that's going to just fall apart your wire if you make it out of magnesium. Platinum is very inert. It's very unreactive. It's below silver and gold in the reactivity series, and it doesn't give a distinct flame when heated. It has a high melting point, which is another important thing. An aqueous solution is suspected to be potassium bromide and is tested for the presence of an anion. Okay, write the name of the reagent used for the test. Well, potassium bromide, I'm using a highlighter here. Very important that you use a highlighter in exams, so make sure you highlight the keywords. Potassium is K plus and bromide is Br minus. What does anion mean? Well, anion is like a contraction. It means a negative ion. So we're looking for a test for the bromide ion, not the potassium ion. So the test for the bromide ion is use acidified silver nitrate. And if you're going to mention an acid, make sure you mention nitric acid and dilute nitric acid. If you mention a hydrochloric acid or something like that, that's going to mess up your test. You can write AgNO3 with an AQ in brackets. That's the formula for silver nitrate solution. And that will get you the mark. State the expected result of this test. Well, the silver ions in the silver nitrate, because they're in solution, they can move around, combine with the bromide ions to form a cream precipitate of silver bromide. Remember, chloride ions give you a white precipitate, which is why we must never acidify it using hydrochloric acid. The formula of the product is AgBrS. Super duper duper. Once again, I recommend you press pause right now on the video, read the question and have a go, and then I'll go through the answers. Okay, so we're looking at hydrogen H3 here. It's saying what are going to be the number of subatomic particles in the isotope H3? Well, hydrogen has one proton no matter which isotope it is. So we're looking number of protons is 1, number of electrons should be 1 as protons equal electrons, and the number of neutrons should be the mass minus the protons. So 3 minus 1 is 2. So that should be fairly easy. The answer would be C. B would be an ion because it doesn't have any electrons, so it'd be a positive hydrogen ion, which they didn't indicate in the question. B, the diagram shows the mass spectrum of a sample of chlorine with one peak missing. Chlorine has two isotopes, Cl35, Cl37. The relative abundance of the isotope Cl35 is 75.5%. The relative peak height of this is 82.5 in the mass spectrum. Calculate the relative peak height of the missing peak caused by the isotope Cl37. So what you really want to do here, they've told us that chlorine 35, it's got a 75.5% abundance, all right? Which means the other chlorine 37 has a 24.5% abundance, 100 minus 75.5. So we have the abundance, but we also have the height. We have chlorine's height. So what I want to work out is how much height do we get for each 1%? So if I do 82.5 divided by 75.5, I'll find out how much height you get for each percent. And then we can just do 24.5, which was the abundance of chlorine 37, times that height, and that will give us the height of the chlorine 37 peak. So we find out if we do 82.5 divided by 75.5 that you get 1.09 height on the graph for each percent. So if we know chlorine 37 has a 24.5% abundance, do 24.5 times 1.09 and you'll get 26.705, and that should be the height of your chlorine 37. Now, it also says, give a reason for the presence, this is in part 2, for the three peaks at 70, 72 and 74. So you've actually got chlorine when it's split into atoms, but also chlorine, of course, can come in as a diatomic molecule, right? So you could have two Cl35s, which make the diatomic molecule, which would have a mass, an MR of 70. Or you could have chlorine 35 with the isotope, which is 37, and that would have a mass of 72. Or you could have chlorine 37 plus another chlorine 37 to make Cl2 with a mass of 74. So that's why we get those three different peaks. Nice and easy, and that should grab you some marks. Okay, let's move down to the next question. Part 3. Explain using calculations why there is an approximate ratio of 961 for the peak heights of 70, 72, and 74. So essentially they're saying, why is it we get chlorine 35, 35, 9 out of 16? Why is it we get 72, 6 out of 16, and 74 is only a 1 out of 16? Okay, so if we look and we say, right, well, 3/4 of all the chlorine in is chlorine 35, then the chance of you getting diatomic chlorine 70 is 3/4 times 3/4. So there's a 3 in 4 chance of a chlorine 35 bumping into another chlorine. The probability is 3/4 times 3/4 that they'll each come together. And that gives you 3/4 times 3/4 gives you 9/16. So that's where we get the 9 from the ratio of 961. Now let's look at the probability of you getting 72. Well, to get 72, one of my chlorine 37s can bump into any one of these 335s. So what's the probability of it being a chlorine 37? Well, that'll be 1 in 4. And what's the probability of it bumping into a chlorine 35? That'll be 3/4. But remember, it could be, I need to double the whole lot of this. So it's 1/4 times 3/4, but I need to double it, okay? Or add 1/4 times 3/4 to 1/4 times 3/4. And we get 6/16. Why do I need to double it? Because one of the 37s could bump into a 35 and one of the other 37s could have bumped into a 35. Now, the probability of a 37 bumping into another 37 is 1/4 times 1/4. So if you have two 37s, then there's a 1 in 4 chance that it will bump, and another 37, which is a 1 in 4, there's a 1 in 4 times 1 in 4, they'll bump into each other, which is 1/16. And that's how we get the ratio of 961. That was clear as mud. But you can just learn it, memorize it. Let's go. Part C, the mass spectrum of a hydrocarbon B, which has a molecular formula CXHY, is shown. Determine the relative molecular mass of B, of compound B. Well, you go to the tallest line on the graph, and that tallest line is 170 here. Sometimes you'll get one at 171, a tiny one, and that will be if there's a carbon 13 isotope in there. So sometimes you get a tiny little, tiny line to the right of the MR. So the relative mass of the compound is 170. Deduce the molecular formula. This is just a little game of let's add it up, right? We know that it's got a C in it and an H in it. So it could be like C6H14. What's that? That's 6 times 12 is 72, plus 14 times 1 is 14. That's 86. Well, that doesn't equal 170. So I need to just play with my carbon and hydrogen until I get to 170. And there's a number of different ways you can do this. The simplest way is just by doing alkanes, where you times 2 plus 2 with the hydrogen. So we go C12, 12 times 12 is 144, know your 12 times table, plus 26 for 26 times 1, and you'll get 170. So that's the simplest way to get to that MR. There are a few other ways to get to that MR if you're not looking at alkanes. All right. Part D, you got 1 gram of a different hydrocarbon. So it's not the same one we just looked at, the C12H26. A different hydrocarbon, W, was burnt in oxygen. Analysis of the combustion showed the complete combustion produced 3.4 grams of carbon dioxide, 1.29 grams of water. Why is it important to use the highlighter? The word complete means all of the hydrocarbon has become carbon dioxide and water. So if we can work out the moles of the carbon dioxide and water, we can work out the formula for the hydrocarbon. Water and carbon dioxide are the only products. Calculate the empirical formula of W. So what I'm doing here, straight away, I'm writing out the equation. And then I'm saying, well, what's the ratio of carbon to carbon dioxide? Now, when you balance combustion equations, you should all know that you just take whatever number is in the hydrocarbon and put that number in front of carbon dioxide. It's 1 to 1. But the ratio of the hydrogens in a hydrocarbon to water is not 1 to 1. okay? Because for every 2 hydrogens you need, or for every one lot of water, every one molecule of water, you're going to need double the amount of hydrogens in the hydrocarbon. So the hydrocarbon will always have double the hydrogens than the water. Take methane above here, right? If you have one methane molecule, it's going to form 2 water molecules, right? The ratio is 2 to 1. Or you see what I'm saying? So you would need 2 water molecules to balance a methane because it's got 4 hydrogens. So anyway, let's get on and work out the empirical formula. So 3.41 grams mass over mR equals moles. So if I do 3.14 over 44, you get the 44 by doing the 12 plus the 32 for the oxygen, and you'll get 0.071 moles. We know it's 1 to 1, so that tells me that I have 0.071 moles of carbon in the hydrocarbon. So that's how many moles we must have started with in the hydrocarbon. Now, if I do 1.29 over 18, that gives me 0.071 as well, H2O. However, I need to times it by 2 because you're going to have double the hydrogen in the hydrocarbon than you do in water. So you're going to have 0.42 moles. Now divide by the smallest for each of these and you'll get the ratio of the carbon and hydrogen. So the carbon is going to be 1 and the hydrogen is 0.142 divided by 0.071. We're going to have 2. So it's 1 to 2. So our empirical formula is CH2. And that's the empirical formula, and that will get you 4 marks. All right, people, smash the like. The more you smash up the like button, the more I can do more of these that will help you out. So question 5, intermolecular forces affect the melting temperature, boiling temperatures and solubility. The table gives the melting temperatures of some of the group 7 hydrogen halides. Predict the melting temperature in Kelvin of hydrogen iodide using the information in the table. Right, well, you can see hydrogen chloride and hydrogen bromide, we've got an increase as we go down the halides. So as we get bigger, these molecules are larger, they have more electrons, therefore they have more van der Waals forces. You might call them London forces, basically stronger intermolecular forces. So we're looking for an increase in melting point. What about hydrogen fluoride? Why doesn't it fit that pattern? That's because hydrogen fluoride is an anomaly. Hydrogen fluoride is one of those rare molecules that has hydrogen bonding as well as van der Waals forces, so its temperature is unusually high for its size. So for hydrogen iodide, the example will accept any number between 200 and 220 for your guess. I'm going for 205, but there we go. All right, let's get on to B. The compounds in the table are isomers. We have hexane, 2-methylpentane and 3-methylpentane. We've been given their structural formula and their boiling temperature. Look at the relationship here. Which is the most likely to be the boiling temperature of another isomer, which is called 2,2-dimethylbutane? The structure of 2,2-dimethylbutane has been given to us. Look at the relationship. We can see the boiling temperature is decreasing with the number of branches. You might say, hold on, but 3-methylpentane's got a slight increase. It's got the same branches as 2-methylpentane. It's just that it's in a different position. So that has affected the boiling point not so badly. So I'm saying that the answer here, because it's got 2 branches, and that is the number of branches is decreasing the boiling point. Well, this is 2 branches, so it's going to have to be lower than 61, and my answer I went for was 50. If you went for 60, that's not low enough, and if you went for 40, that's too much disruption for just an extra branch. Right, methanol, CH3OH, is miscible with water in all proportions. Sodium chloride is much less soluble in methanol than in water. Explain these statements using your knowledge of the interactions between the solutes and the solvents. You must use diagrams to illustrate your answers. 6 marks. Jeez. Okay. So what we have to think about here is what is special about the methanol and about its ability to mix with water. Well, methanol has oxygen and hydrogen, and so does water. Guess what? They're both polar molecules. They both can do hydrogen bonding because they contain a bond of oxygen bonded to hydrogen. some molecules contain oxygen and hydrogen, but they're not bonded together. Don't get mixed up. They can't do hydrogen bonding. But water and methanol can both do hydrogen bonding, and they're of roughly comparable strengths. So that means that the water is quite happy to mix with the methanol instead of another water molecule. It's quite happy, and they form a bond angle of 180 degrees. Just another random fact you've got to know, and sort of drawing this diagram with a brief explanation will get you 3 of the 6 marks, basically. So methanol and water are both polar molecules. I like to say they both can do hydrogen bonding is on the mark scheme. A correct diagram of it. Mine's a bit puppy, but there we go. Um, don't write hydrogen bonding like I did there. Yeah, so they both contain OH bonds, and they both can do hydrogen bonding. And the hydrogen bonds that the methanol forms with the water are relatively comparable in strength to the hydrogen bonds that a water will form with another water molecule. So it's not losing out by bonding to the methanol instead. Okay. And now, if, for instance, the hydrogen bond that the methanol forms with the water was not as strong or not as stable as the ones that water molecules can form with each other, then the chances are the water molecules will not form many of these hydrogen bonds with the methanol, as they're looking for stability. Bit late. Okay. However, if we look at methanol now, what are we looking at next? Oh yes, we've got, what was the other? Sodium chloride. So now if we look at the sodium chloride, you know the formula of sodium chloride is NaCl. And you should know that sodium chloride forms a giant ionic lattice with very strong ionic bonds. However, the energy released from the hydration of the lattice, that means breaking apart the Na plus and the Cl minus to use those ionic bonds, the energy released is sufficient to overcome the hydrogen bonding between the water molecules, which means that the water molecules can surround an Na plus or surround a chloride ion. And water can only do this because it's polar. So it has a positive bit on the hydrogen and a slightly negative bit on the oxygen. So the negative bit on the oxygen of the water molecules can go towards the sodium ion, and the positive bit on the hydrogen can go towards the chloride ion. And so the water molecules can surround these ions. And it has to be energetically stable. So it just so happens that when you work out all the checks and balances and calculations, it works out that hydrating sodium chloride is more energetically stable than the water staying with its hydrogen bonds and the sodium chloride staying with its strong ionic bonds in a lattice. So therefore the ionic bonds and the hydrogen bonds are both overcome by the energy or enthalpy of hydration, the energy released by hydrating those ions. However, in methanol, the hydrogen bonds are not stronger than the ionic bonds. So to break those bonds in the methanol and to break the ionic bonds in the sodium chloride, it just doesn't work out energetically worthwhile. So essentially, the energy of hydration of sodium chloride, if you hydrate the sodium chloride with methanol, it's not enough energy to overcome the hydrogen bonds between the methanol and the ionic bonds in the sodium chloride. So you could say that the methanol doesn't form strong enough hydrogen bonds. There's not enough energy released when you break those bonds and you remake the bonds with the sodium chloride. That energy is not greater, so it doesn't happen. And there we go. Let's move on to the next question. You might ask yourself, why is methanol not as polar as water? Well, it's got that non-polar, that CH3, that methyl group. Of course, ethanol's even worse because it's got an ethyl group. So essentially, it's not as polar, and therefore it cannot overcome the hydrogen bonding that it forms. It cannot overcome the ionic bonds in the sodium chloride. It will dissolve partially or slightly, but not fully. All right, what have we got to do here? We've got to complete this table on bonding. So the first one here is potassium chloride. What type of structure does it have? Well, you should know potassium is a metal. Chloride is a non-metal ion. Therefore, it's ionic, the type of bonding. And what is the structure that all ionic substances have? They all have a giant structure. So we're looking really here for ionic as the bonding and giant as the structure. Now, our next substance is iron. What's iron? Is it a metal or non-metal? Well, it does tell us the bonding's metallic, so we know it's a metal. All metals have a giant structure. Um, So giant metallic bonding. Now iodine, you know that's a non-metal and it's in its elemental form. Means it's going to be, is it going to be a simple covalent? Well, it is in this situation. And we can really see that from the melting temperature, 387 Kelvin. It's got a very low melting point for a solid. So it's a simple covalent structure. Okay, explain why the melting temperature of silicon oxide is much higher than that of iodine, even though the bonding is both covalent. The bonds in iodine are pretty strong. They're probably comparable to the silicon 4 oxide. Okay, they're probably comparable. So it's not really down to the covalent bond strength of each. It's down to the fact that iodine is a simple molecule. So when we want to melt iodine, we just need to overcome those weak intermolecular forces between the molecules, which will be London forces or Van der Waals forces. We just need to overcome those temporary dipole-dipole forces between the molecules. And if we overcome those temporary weak forces, you can melt iodine. If you wanted to melt silicon oxide, it's a giant structure. That means you've got to overcome many strong covalent bonds, which requires a lot of energy to break. And there's your answer. If you wanted to throw in the definition of a covalent bond, you've got to overcome many electrostatic forces of attraction between shared electrons and nuclei. You could say that. But on the mark scheme, you don't need to put that. So that's the difference. Lots of energy to break all those strong covalent bonds when you're trying to melt silicon oxide. When you're trying to melt iodine, you're actually not trying to break those strong covalent bonds within the diatomic iodine. You're actually trying to break the weak intermolecular forces between the iodine molecules. Don't forget at the start of each question to hit the pause button, have a go at the question, and then you can watch the walkthrough yourself. Just grab a scrap bit of paper when you're doing these walkthroughs, have a go at the question first, and then you can go through, press play while you're sitting there and check your answers off. Good way to do a test. Makes it different than just doing it off the internet. You get the audio as well. So if you like these, leave a comment and I'll do the rest of the papers for Edexcel Chemistry and biology. I haven't done any bio ones yet. All right, let's move on. We're going to move on to the next question. So, part C. The iron and potassium chloride both conduct electricity when molten. However, only iron conducts electricity when solid. Pause it, have a go. Explain these observations. So, iron contains delocalized, that's not how you spell delocalized. Iron contains delocalized electrons, right? It's a metal. All metals contain delocalized electrons. So does graphite, which is carbon. Um, Iron contains delocalized electrons, and these electrons carry charge through the structure, whether it's liquid or solid. However, potassium chloride contains no delocalized electrons to carry charge, but when you melt it or when it's molten, its ions are free to move and carry charge. So it can conduct when molten, but when in a solid form, when potassium chloride is in a solid ionic lattice, the ions are not free to move and carry charge. Hence, it can't conduct electricity when solid. And it doesn't have delocalized electrons, which can carry charge through a solid structure. Cool. Okie dokie. Question 7. This is about S block elements and some of their compounds. Which list only contains S block? You're really looking at group 1 and 2. Go look in your periodic table. The S block is group 1 and 2, things that end in 1s2, 2s2, or 3s2. So you're really looking at any elements that end like that. So aluminium's in group 3, we've got to get rid of that. Cobalt is a transition metal. Chlorine is in group 7, we've got to get rid of that. So really, if we look at D, it only contains group 2 and group 1. You've got radium, barium, rubidium, and beryllium. They're all from group 1 or 2. So they're all going to be S block. Which pair of statements describes the trends down group 2? Well, I always try to remember barium sulfate because they like to ask that as a meal. Barium's right at the bottom of group 2. Barium meal or barium sulfate is used in medical imaging because it's insoluble, because it's a precipitate, coats the organs and absorbs X-rays. So if you know that barium sulfate is insoluble when it's at the bottom of group 2, we know that solubility decreases down group 2 of sulfates. But you have the opposite pattern with hydroxides. So the hydroxides increase in solubility down the group. So magnesium, which is right near the top of group 2, is fairly insoluble, magnesium hydroxide. We use that as an antacid as well, neutralizes stomach acid. Okay, anyway, there we go. Solubility of sulfates decreases and the hydroxides increase. So barium hydroxide would be soluble, but barium sulfate wouldn't be. Right, C, the S block nitrates undergo thermal decomposition. Draw a dot and cross diagram for the nitrate 5 ion, NO3 minus, showing the outer electrons only. So what you need to do here is just plop all your electrons on and learn this one off by heart. So for the most part, your oxygens have 6 electrons in their outer shell. Your nitrogen has 5 electrons in the outer shell. But one of the oxygens, where do we get the negative sign? One of the oxygens, it has an extra electron that it took from whatever element that nitrate is joined to. So say it was sodium nitrate. The nitrate ion, it's got that electron from that metal element or whatever element, ammonium or something that it's joined with. So I can show that here as a little triangle. That electron there on that oxygen has come from somewhere else. Okay, what have we got to do here? Write an equation for the thermal decomposition of lithium nitrate. State symbols are not required. Now I'm going to write the incorrect version of the equation first. So LiNO3, lithium nitrate. We might say, oh, that breaks down to this molecule, LiNO2. But it tells us in the next part of the question that the equation below here is. So if you haven't realized, that should be a reminder that this equation is different. And this one forms lithium oxide, nitrogen dioxide, and oxygen. And we just need to balance this all up. Is that balanced? I've got 2 lithiums, 2 NO2. Yeah. Yes. There we go. You just got to learn those equations off by heart, guys. Part 3, the equation for the thermal decomposition of sodium nitrate is different than that of lithium nitrate. The gas produced was collected in a gas syringe, so I've got half a mole of oxygen here. Calculate the theoretical volume of gas in centimeter cube that could be collected at 298 K, and 101 kPa for the decomposition of 0.500 grams of pure sodium nitrate. Give your answer to 2 sig. And we're using PV equals nRT, where R is 8.31. Okay, so do I want to do nRT over V? No, we're trying to find V. So in order to find V, I need to divide both sides by pressure, and I'll get nRT over P equals V. So we know that R is 8.31. We know the temperature is 298 K. We know the pressure underneath is going to be 101,000, because you need to be in pascals, not kilopascals, in the ideal gas equation. And we know that N here, the moles, we can work out by mass over MR or AR times moles. So we want to do mass over MR. Well, we've got 0.500 grams of sodium nitrate. Sodium nitrate is 23 for the sodium, 14 for the nitrogen, and 48 for the oxygen. So let's add all of those up. What does that equal? 33, 37, 85. Okay, so we do 0.500 grams over 85, and that's going to give us our moles of sodium nitrate. And then all we've got to do is take the moles of sodium nitrate, times it by 8.31, times it by 298K, and divide by 101,000. Now, if you're no good at sticking stuff in your scientific calculator, break it down. Do your moles times 8.31 times 298K first, write that answer down, then do the divide by 101. Now, at this point, we can half these moles. Half, you say? Why half? Remember, the gas collected was only a half. Have a look up there. I've circled the oxygen in the equation. It was only a half. So technically, there's a 2-to-1 ratio of sodium nitrate to oxygen, and we're supposed to be working out the volume of gas that would be created. So we've just worked out the moles there based on the sodium nitrate, but the sodium nitrate was double the amount of gas formed. So it's going to be half 5.8 at some point. You can either work it all out and then half the answer right at the end, and you'll get 72 centimeter cubed. Now, why 72? Remember that volume in the ideal gas equation is always in meters cubed. So if you want to turn back to centimeters, you times by 1 times 10 to the power of 6. Normally, it's the other way. You're going from centimeter cubed to meters cubed. So you divide by 1 times 10 to the 6. Okay, state one reason why the experimental gas volume may differ from the calculated theoretical volume. Well, why the gas volume may differ, if you assume that none has escaped from the equipment, is the sodium nitrate did not fully decompose, or they didn't heat it long enough for it all to react or decompose. A textbook states the thermal stability of group 1 carbonates is generally higher than the thermal stability of group 2 carbonates in the same period. Explain why group 1 carbonates are more thermally stable. So if you heat a group 1 carbonate like lithium carbonate or sodium carbonate, it's not going to break down as quickly as magnesium carbonate or calcium carbonate, the group 2 carbonates. And this is kind of counterintuitive, because we'd normally think, well, group 2, they've got a +2 charge, right? They're going to hold on to the carbonate ion, which is negative, a lot more strongly. But we got something else going on here. So you're absolutely right. A group 2 +2 charge in first glance should hold on more strongly, but it doesn't hold on to the carbonate or the bonds as strongly. And the reason is the lower charge in the group 1 metal ions means they have a lower charge density, okay? And they have less of what's called a polarizing effect. So the carbonate holds its spherical shape more, and the bond is less distorted. However, the magnesium 2 plus has a higher charge density. That means for the size of it, there's a lot more positive charge within each volume part of the magnesium ion. And this means it stretches the carbonate ion out and weakens the bonds between the carbon and the oxygen, because it's pulling the oxygen atom, one of the oxygen atoms in the carbon, towards the magnesium. And that is weakening the bonds and making it more likely to break and form magnesium oxide. So basically, it's stretching. What we say here is it has a higher charge density, it has a greater polarizing effect, and therefore it distorts or disrupts the bonds in the carbonate ion. And that will get you the 3 marks, what I just said there. So what does that mean in effect? It means that the magnesium is pulling one of the oxygens in that carbonate ion so close to it that it's going to snap off and form magnesium oxide and release carbon dioxide. All right, let's go. Moving quickly. Okay, question 8. This question is about some reactions of chlorine and hydrogen chloride. When hydrogen gas and chlorine gas are mixed and passed over a hot platinum catalyst, hydrogen chloride gas is formed. The equation for the reaction is H2Cl2 goes to 2HCl. In an experiment, we got 20 centimeter cubed of hydrogen and chlorine, and they react together. All gas volumes are measured at RTP. So that means at RTP, your volume of gases are equivalent to moles, essentially. Um, and we've been given Avogadro's constant, lovely jubbly. So if we have 20 centimeters of hydrogen and it's in a 1:2 ratio with the hydrogen chloride, we're going to end up with 40 centimeters of product. Now the question here says calculate the number of gas molecules of the product. So we know we've got 20 centimeters of hydrogen and chlorine, and they're going to come together to make 40 centimeters of hydrogen chloride because they're in a 1:2 ratio. And so we want to find out how much product we've got in moles. So we do 40 divided by 24,000, because it tells us 24,000 centimeter cubed equals 1 mole. And that gives us 1.66 times 10 to the minus 3 moles. That gives you 1 mark. Now we have the number of moles. We just need to times by Avogadro's constant, which is the number of particles in 1 mole. So times 1.66 times 10 to the minus 3 by 6.022 times 10 to the power of 23. And we get 1.033 times 10 to the power of 21. And that's the amount of particles in the product. Part B, hydrogen chloride gas dissolves in water to form hydrochloric acid. Hydrogen chloride gas does not conduct electricity. Hydrochloric acid is a good conductor of electricity. Give a reason for the change in conductivity. Well, essentially, when hydrogen chloride is a gas, it's covalent, right? It's sharing electrons. There are no delocalized electrons and no free ions. You have to have either delocalized electrons or free moving ions to conduct electricity. When hydrogen chloride dissolves in water, it fully dissociates. You remember that from GCSE. It's a strong acid. So we end up HCl goes to H plus Cl minus. I should put an AQ here for state symbols, but there we go. So as it fully dissociates and becomes ions, the ions are free to move and carry charge, and that's why it conducts electricity. Whereas when it's a gas, it's covalent. So no free ions. Okay, when concentrated hydrochloric acid on a glass rod is held above a concentrated ammonia solution, white smoke is observed. Write an equation including state symbols for the reaction that produces the white smoke. So it's going to be HCl plus NH3, so hydrogen chloride plus ammonia, and that is going to go to ammonium chloride, NH4Cl. We're tempted at first to put HCl with AQ because HCl is an acid, but actually they're saying they're holding the glass rod above, so it can't be that the solution of acid is mixing with the glass rod. It's the vapors of hydrogen chloride that are rising up and reacting with the ammonia. Okay, or the other way around. The vapors are coming together. Hydrochloric acid is added to a test tube containing a sample of solid sodium carbonate. Give two observations. Right, what happens when you do an acid and carbonate? You get carbon dioxide, so you're going to see bubbles. What color are group 1, 2, 3 compounds, i.e. the carbonates are group 1, 2, or 3? They're all white solids. And what's going to happen? That's going to disappear because group 1, 2, and 3, when they become soluble and they dissolve in solution, they are going to go colorless. So you're going to see a white solid disappear and bubbles of CO2 gas. And you cannot say, oh, I'll see carbon dioxide. How would you tell it's carbon dioxide? So say you'll see effervescence or bubbles and you'll see the solid disappearing, a white solid if it's a group 1, 2, or 3 compound. Describe an experiment to enable you to accurately determine the concentration of approximately 1 mole per decimeter solution of hydrochloric acid using a solution of sodium hydroxide of 1 mole per decimeter. Details of the calculation are not required. This is essentially giving you the core practical from GCSE. It's essentially just saying, explain how to do a titration without doing any calculations. So there's loads and loads of things. You could go into super detail here, but it's only 5 marks. So 1 mark, use a pipette, which is the most accurate way of transferring volumes in chemistry. So use a pipette to transfer 25 centimeters of hydrochloric acid to the conical flask. That's your unknown solution. That's roughly 1 mole, but you're not sure. Add a few drops of phenolphthalein. You need to name an indicator and state the color change. So it's going to be colorless in acid. I should really put it will go pink on neutralization, which I forgot to put here. Now we're going to fill the burette with sodium hydroxide solution. Ideally, you'd also write wash the solution with the 1 mole per decimeter sodium hydroxide. You'd say wash the burette with the same concentration that you're going to fill it with. You don't do the same with the conical flask. You wash that with distilled water. Anyway, you could mention carry out a rough titration, which is where you find the rough endpoint. And next time you repeat, and because you have an idea of the endpoint from your rough titration, you repeat, and then as you approach the endpoint, you slow down and add dropwise, using the tap to carefully just add drop by drop, making sure you swirl the conical flask after each drop. Remember, a conical flask is used instead of a beaker because you're less likely to lose any of your reactants. When the color changes, it will go pink here. Okay, so when it goes pink and stays pink, if you just stop as soon as it goes pink, you won't get the right accurate answer. You need to wait until it definite color change and stays pink after swirling. Then you can record your result and then repeat until you get concordant results. Now there's enough here, even though there's probably another 10 points we could make. We could say use a white tile to check, make the color change easier to identify. We could say rinse, do your rinsings. Like, so you're going to rinse the end of the burette into the conical flask. You're going to rinse the sides of the conical flask to make sure all the reactants have got down. And you're going to do your rinsings with distilled water, but you're going to rinse the burette with sodium hydroxide. And you rinse the conical flask with distilled water before adding the acid. And there we go. Right, let's go part C. Chlorine can be produced by reacting concentrated hydrochloric acid with magnesium 4 oxide. The equation for the reaction is here. Deduce the half equation for the formation of chlorine. You know this one from electrolysis. It's your chloride ions, right, going into chlorine. Chlorine's diatomic, so it's going to release an electron, two electrons, and then we're going to need two chloride ions to form one chlorine molecule. And each chloride ion is going to release one electron. So that's your half equation for the formation of chlorine. Now, a student reacted 5 centimeter cubed of 5 mole per decimeter hydrochloric acid with an excess of manganese 4 oxide. 70 centimeters of chlorine gas were produced. The teacher said the expected percentage of the experiment, the expected yield of the experiment was 75%. Determine whether the student achieved the expected percentage yield. Okay, so what we want to do here is, first of all, we've been given the hydrochloric acid, which is reacted with an excess of magnesium oxide. So we can't use our magnesium oxide to work out how many moles of chlorine we should have got. So first thing to do, we told we got 70 centimeters of chlorine gas. We can turn that into moles later. We want to work out how many moles of chlorine gas we should have got. So theoretical. So first of all, work out your moles of hydrochloric acid. 5 over 1,000 to get into decimeters times the concentration of 5. Remember, we're doing V times C equals N. That gives us 0.025 moles of hydrochloric acid. Now go upstairs to the equation and check the ratio of hydrochloric acid to chlorine gas. It's a ratio of 4 to 1, which means therefore we should have 4 times less chlorine gas formed. So we need to do 0.025 divided by 4, right? No, Newell, not times by 4, you idiot. So we want to write divide by 4. So, yeah, 0.025 divided by 4, because you're only going to get a quarter the amount of chlorine than you had hydrochloric acid. And so we should make 6.25 times 10 to the minus 3 moles of chlorine gas. That's how much we should get. Now let's look at how many moles we actually got. So theoretical should be 6.25. That's the maximum we can get because our limiting factor is our hydrochloric acid. How much did we actually get? Well, we actually got 70 over 24,000 because we made 70 centimeter cubed. We can turn that into moles by dividing by 24,000. So the actual moles were 2.9 times 10 to the minus 3. Now we're told we need a yield of 75%. That's the expected percentage yield. It's not a bad yield. It's not great, to be honest with you. So now what we need to do is check, did we achieve 75%? Don't look like it. Do 2.9 times 10 to the minus 3 over 6.25 times 10 to the minus 3 and multiply that by 100. And that's going to give you your percentage yield. And is it 75%? And if it isn't, we need to state, no, we didn't achieve that yield. Some of those really stingy examiners, when they're marking your paper, you get all the calculations right, but they'll say, oh, they didn't say no, they didn't achieve the expected yield, and then take 1 mark off just because you didn't say no. So, yeah, that would be a pain in the backside. So just write, no, they didn't achieve. Okay, we're near the end of this paper now. So we're going to move on. Crack on, get this paper done. You can check out some of my other videos. Most of them have been on AQA, Chemistry A-Level and Biology and GCSE. But I'm starting to work through the Edexcel ones now. D. Chlorine reacts with hot concentrated aqueous sodium hydroxide to produce sodium chlorate 5 as one of the products. The equation for this reaction is shown. Explain using oxidation numbers why this is a disproportionation reaction. Ooh. That's where one species can be both oxidized and reduced at the same time. So if we look at chlorine, elemental state, oxidation state is 0. What is the oxidation state of chlorine in sodium chloride? Well, sodium is a group 1 metal, will always be +1. So the chlorine is -1, or the chloride is -1. So what's happened to it there? Well, it's gone from 0 to -1, so it's gained electrons. It has been reduced. However, in sodium chlorate, NaClO4, 3, the oxygen has a total of -6 because each oxygen is always -2, and the sodium is +1, which leaves the chloride ion as +5 in sodium chlorate. So this shows that the chlorine atoms in the chlorine molecule were both oxidized and reduced. Some of them gained electrons and some lost electrons. And that's why it's called a disproportionation reaction. Okay, oxygen is always my go-to when working out oxidation states because oxygen is always -2 with every element in the periodic table, and it's so common in the compounds on Earth. Oxygen is found in most of the chemicals we do in chemistry, so always start with the oxygen. You know that's -2. Yeah, if it's with fluorine, which is the only other more electronegative element in the periodic table, then oxygen can become positive. So that's an exception, but it's rare that it's with fluorine. Okay, now it says calculate the atom economy by mass of sodium chlorate 5 in this reaction. And this is a 3 marker. So what we want to do is just put that reaction up and work out the atom economy. Now, the way to do atom economy is the useful product, which they've told us here is sodium chlorate 5. And we can do that over the total mass of all the products. So that's one way to bust this out. So sodium chlorate equals 106.5. That's the 23 for sodium, 34.5 for the chlorine, and 48 for the oxygen. And then to work out the mass of all the others, I've got to do the 106.5 for the sodium chlorate plus 3 times 18 for the 3 H2O molecules. You remember hydrogen's 1, oxygen's 16, so H2O is 18. And then I need to whack in 5 times 58.5 for my sodium chloride. Okay, so I'm going to divide 106.5 by, what does this equal? Oh my gosh, get out the calculator. I hate this kind of thing. So what is it? Is it 106.5 divided by, is it 453? I'll just tapping that in. Bada bada bing, bada bada bang, bada bada bing, bang, boom. Yep. Okay. So we want 106.5 divided by the total mass, which I believe is 453. You might need to double check that. And then that's going to give us a decimal, and we need to times that by 100 to get our atom economy. And that's going to equal 23.51%. Did they ask for 2 sig? You could leave it as 23.51, or you could just leave it as 23.5. Calculate the atom economy. We've done this question. What am I doing? Let's zing. We might be towards the end now. 9. Water gas is a fuel gas consisting of a mixture of carbon monoxide and hydrogen. Water gas is produced by passing steam over white hot coke. The equation for the reaction is shown. H2O plus C goes to carbon monoxide plus hydrogen gas. Calculate the total mass of products when 1000 kilogram of steam reacts completely. So, should be nice and easy. You've been given grams, you've been given kilograms, turn it to grams. Let's bust out moles and find out how many moles we have of steam. So we have 1000 kilograms, that's 1 times 10 to the 6, so a million grams. We don't need the S there for grams. Oops. Okay, so that's a million grams because you times it by 1000 to get into grams. So 1 and 6 zeros, or 1 times 10 to the 6 grams. Now we need to divide that by 18 to work out the moles of steam we started with. Well, we don't even need to work out the moles of, yeah, once we know the moles of steam, we know the moles of carbon. Carbon has a mass of 12, an MR of 12. We can work out how much carbon we needed. And then we know the total mass of products formed. Beautiful. So this gives us 55,555 jeez, moles of steam. So if I have that many moles of steam, how many moles of carbon do I have? Well, the whole thing's 1 to 1 to 1. So I just need to work out the moles of carbon. So if I have that many moles of steam, which equal 1,000,000 grams, I've got 55,555 moles of carbon. I need to do 55,555 times 12, and that'll tell me how many grams of carbon were used. So, um, yeah, beautiful. We don't need all this garbage I'm writing down here. We just need to work out how many grams of carbon and then add it to the grams of steam that we've already got. It's simple enough, dude. So I just want to find 55,555 times 12, which is the MR of carbon. 6 on my calculator. Never mind. And that's going to give us our grams of carbon. Do they want the answer in kilograms? Calculate the total mass. Doesn't really matter, I don't think, whether you do it in kilograms or grams, but we're going to get 666,672 grams. So we got 666,672 grams of carbon are needed to fully react with the 1,000,000 grams of water. So now add the grams of carbon and water together, and that's your total mass of reactants. We know that the mass of reactants is equal to the mass of products as the law of the conservation of mass. So we should have 1.6 million roughly, where 1,666,672 grams. You want to divide that by 1,000. We're going to say our total mass of products is 1,666 kilograms, or 1,667 kilograms. So you could put the answer in grams, you could put it in kilograms. It doesn't really matter, as long as you have the total mass of the reactants, which we've worked out here, then you also have the total mass of products. There we go. Now, is that the end, or is there another question? That is the question. Okay, one last part to this question. I just believe there is part B. So let's shift downwards, please, Bob. I'm going to have to shrink this up. B. The complete combustion of water gas produces carbon dioxide and water. A student drew a diagram of the apparatus to attempt to identify the combustion products. Looks pretty good. We've got a boiling tube with lime water. That's going to detect your CO2. And then we have the anhydrous copper 2 sulfate. That's that white solid that turns blue when water touches it. Kept in an ice bath so that the water vapor will condense as it comes through. So evaluate whether the student's apparatus is suitable. Well, it is and it isn't. We want to say the good things about it. Lime water's going to turn cloudy and tell us that we've got carbon dioxide. That will get you 2 marks. I know, unbelievably easy marks, eh? Lime water goes cloudy, which tells us the presence of carbon dioxide or identifies carbon dioxide. It's 2 whole marks. And then anhydrous copper 2 sulfate, which is a white solid, will turn blue on contact with water, identifying the presence of H2O. Is another 2 marks. Oh my gosh, 4 out of 5. What a beautiful question. But what's the mess up here? If the water vapor is coming from the water gas up that tube into the lime water, what's going to happen? Yeah, we can't be sure whether the water we're getting in the U tube is from the lime water or whether from the water vapor. So we can't really be sure of the source. So you should place your U tube before the lime water. You want to test for the water first and then have the lime water after, because it could be that my lime water is heating up. Some of the water within the lime water is evaporating and going into the U tube, and I'm believing that water is part of the product when it isn't. So that is the mistake here for the 5th mark, which is quite a hard one to get, but the U tube should always come before your boiling tube with the lime water. Okay. Thanks for watching. Let's get to the marks.
You're still here? It's over.